All right, class, for part 2 of chapter 8, we're going to be looking at extrapolation. So linear models give a predicted value for each case in the data. That's what they're used for, to be able to make predictions based on data that we have. But we can't assume that a linear relationship in data exists beyond the range of the data that we have. Because things could be going on that change the situation later in the data. It depends on what your x value is. If you're talking about time, things could change in the future, or just the way things act could change as you have more of them. So the farther from the new x value is from the mean of the x, the less we should trust the predicted value, the less trust we can place in it. So once you venture into new x territory, that's called an extrapolation. It's a prediction that is outside of your data. And one of the things you do with this, because a lot of times x variable is going to be time. Like as time goes on, what happens to another variable? And if you're predicting in the future, that's going to be an extrapolation. An extrapolation is an attempt to peer into the future. And we know that's a dangerous thing to do, but it doesn't stop people. They try to predict things based on the past. And a lot of times in a given situation, that's just not going to work. So here's some more realistic advice. If you have to extrapolate into the future, at least don't have 100% confidence. Don't completely believe the prediction will come true. Now, when we were extrapolating for Barbie Bungee, that's a little bit different because of the situation. Think about the situation. We just added a rubber band every time. You kind of expect it to go down by a certain amount every time based on that rubber band. That's pretty consistent as you add rubber bands. So the extrapolation wasn't that bad. We don't start doing like random crazy stuff as you put more rubber bands on. But let's look at something like this. So the Energy Information Administration made predictions based on their models on the prices of oil barrel prices. So if you look at the actual price, though, here in orange or red, yeah, that looks like orange to me. You can tell they're way off. Like they're trying to make a prediction, but you just can't predict what's going to happen in the future with something like that. There are situations where you can be a little more confident about what you're predicting for the future, but stuff like this, you really can't do it. And a linear model is just not going to work except in that given time period. You could come up with predictions. So yeah, the situation could change. Like if you have like in this picture right here, one specific day that you got married, you couldn't extrapolate that you're going to get married every day for the rest of your life. At least I hope that you're not going to get married every day for the rest of your life. So yeah, you got to take into account the situation that you're in and realize sometimes that data can only be used in that specific situation or time period. The Chapter 8, number 27, I will cover that in a separate problem, so we will get back to that one. Okay, so lurking variables and causation. This is another thing you have to worry about when you're looking at these linear models. No matter how strong the association is, and no matter how large your R-squared value, no matter how straight the line, there's no way to conclude from a regression alone that one variable causes the other. It can give you data leading that way, but you can't come to that conclusion just based on the data that you have. There's always a possibility that some third variable is driving both of the variables you have observed. And in science, they have to check for the other variables and take them into account. And it's a much, much, much more complex calculation than what we're going to do in this class. We're going to just focus on the one variable in here. So an extraneous or lurking variable is not explicitly a part of the model, but it definitely affects the variables in the model and how they appear to be related. So let's give an example on that. Here we have a scatter plot that shows the average life expectancy for a country is related to the number of doctors per person. It's a positive correlation, right? As you have more doctors per person, the life expectancy goes up. Now, I could see that one actually having a cause, a causal effect, right? Having more doctors might actually help with life expectancy. I see that. That one makes sense to me, right? So this correlation does make sense, but let's take a look at this one. We have another scatter plot here. And this one is true as well. There is a positive correlation here as you have more televisions in a country, the amount of televisions per person, as it goes up, the life expectancy goes up as well. But what conclusion can we come to based on that? Are we saying that, like, as you buy more televisions, your life expectancy goes up? So since televisions are cheaper than doctors, let's go ahead and just send TVs to the countries with low life expectancies to get their life expectancies up, right? That makes sense, right? Looking at the variables. But the reality is you got to consider lurking variables. It makes more sense. You got to find what makes more sense. You got to be logical with this kind of stuff. So countries with higher standards of livings have both longer life expectancies and more doctors, and they also have more televisions. They have more jewelry. Maybe jewelry's causing us to live longer. So if higher living standards cause the changes in these other variables, so it's more than likely the living standards that are causing the changes in the variables. So improving the standard of living might expect to prolong lives and increase the number of doctors and TVs. So that linearity does not imply causation. And that is the end of the slides for Chapter 8. That is Part 2. And this is your homework. It'll be on the sheet itself, and I will make separate videos for the homework problem.